Okay, let's get started, everyone. Yeah, welcome to this lecture. This is the second part of our introduction to deep learning. And yeah, this is quite a lot of material in this lecture, so hopefully we'll get through it, but if we don't, we'll carry on next week as well. Okay, so let's just recap last week's lecture. So the first thing, or the most important principle that I try to tell you is, even though neural networks, there are many different neural networks out there, convolutional networks, fully connected networks, ResNets, transformers, etc. What I really tried to convince you was that neural networks are simply flexible functions that are fit to data. And this is pretty much true for every kind of network that's out there and the way that you train it as well. So I introduced two different types of networks. The first is probably the most basic, which is the multi-layer perceptron, or also known as a fully connected network. And then I also showed you a really, really popular architecture, which are these convolutional neural networks. And they rely on these kind of spatial correlations in the images and sharing of weights. And I also showed you some of the kind of important tasks that we use deep learning for. And so, for example, regression, where we're just trying to fit a line to some data. Classification, where we actually want to predict the probability that the input is with some class. And then we also talked about unsupervised learning techniques. But remember, I said these were all trained in the same way. You still have a loss function and inputs and outputs to the network that you match to. It's just the way that you get those outputs or those labels is kind of different to supervised learning. And so feature learning is trying to learn some sort of salient features of the input. Generative modeling is like, given some training data, can we generate new samples from that data distribution? And then kind of autoregression is like the task of prediction, like given previous values, can I predict into the future? Okay, and then we talked in more detail about actually how we train neural networks. And so we said neural networks are trained using gradient descent. So we just have, you know, for regression, we have this mean squared error loss function. And we just get derivatives with respect to its parameters and then, you know, take a step in the gradient direction. And then I showed you an efficient way of actually computing those gradients. And we know that because neural networks are just composed functions, so lots of functions composed together, we can just use the chain rule to get the derivative of the network with respect to its parameters. And then we made that more general, and we said, oh, actually, we can do this general idea called auto differentiation. And this is a really powerful technique that allows you to get like gradients of any kind of, or nearly any function that you can write in an auto differentiation language like PyTorch or TensorFlow. And it does it by constructing a graph and message passing of these vector Jacobian products, which are the kind of really core thing that we want to compute inside our chain rule. Okay, cool. So where are we at? So like I said, this is the second lecture in our two parts of Introduction to Deep Learning. Before we go on to more scientific machine learning techniques. Okay, and I showed you this at the start of the last lecture. We should hopefully get time to tell you actually how a state-of-the-art model works. So I'm going to show you how ChatGPT works, the architecture that it uses, and how it's trained as well. And you should actually see, even though this seems like a really complex model, it's actually fairly simple to understand given all the stuff that we've learned. Okay, so what is this lecture about? There's a common theme. And the theme is the difficulty of actually fitting neural networks to data. So I said in the first lecture, neural networks have this amazing property that they're universal approximators. So they can, in theory, they can approximate any function. But in practice, this is really hard to do for many reasons. And I'm gonna talk you through all those different ways in which it's difficult to fit functions and the way some of the strategies that we use to try and improve the accuracy of neural networks. So we'll talk about challenges of function fitting and then kind of different ways to improve the accuracy of the networks. Okay, so let's think about how do we measure the error or the performance of neural networks once we've trained them. So this is really, really important, and this is often overlooked. So definitely take in this slide. So everything up to now, I've just said that we've trained neural networks using some loss function. And so I'm just going to take as an example this supervised regression task, like fitting this line to a polynomial. And we have this training data, and I said before, maybe it's noisy. So there's some Gaussian noise, for example, on our blue points, which are our training data. Okay, so then we train this using the mean squared loss function with that training data set that has n examples. But then when we come to actually use the network, we want to test it. And what we need to do, and what is really important to do, is to test your network on points that are not your training points. So then you create a new data set, we call it a test data set, which has n data points. And you can see it's the orange points here. So they're different points. And then we can come up with two kind of metrics of error. One is our training error. So basically our final performance on the training data set. And then our test error, which is our performance on the test data set. And you can notice here, we don't have to choose the same kind of loss function or a metric, if you like, when we're doing our training error and our test error that we used in our training. So for example, in the training, I use the mean squared error. In the training, the test error, I'm using like an L1 norm. So just basically the absolute error. And actually, we're very free to choose what we want for the training loss and the test and the train error. It really depends on your problem, and there are many other metrics that you can use to kind of test the performance. And typically, if you're going to really test the performance of a network, you'll choose many metrics. Some of them might be based on downstream tasks as well. Okay, so let's do that for a neural network trained to fit this data. And I'm going to train 3 different networks. On the left-hand side, it's going to be they're all fully connected networks, so MLPs. And the left-hand side is an MLP that has 1 layer without an activation function. So this is just a linear model, y equals w times x plus the bias. So it's trying to fit a linear model to this. Then I'm going to add another layer. So then the middle one is 2 layers with 16 hidden units. And then the final one is even more parameters, 3 layers, 32 hidden units. And so then what I plot is on the top here, the test error and the train error as a function of the training step. So this is a really important slide to really understand kind of deeply when you're training neural networks, because it's true for every network that you train. And what we get is when we train the left-hand side model, that's just a linear model, we can see it underfits the data. So both the training loss and the test loss are very high, and they're very similar. Then if you pick a model that's more expressive, more free parameters, maybe just the right amount of parameters, we can see that we fit the underlying exact function, so this polynomial, really nicely, and our train and test error are both quite similar, and they're fairly low. So this is what I would call the ideal model. We've really got a model that generalizes nicely from our training data to our test data. And then the final model, we've got loads of parameters in this model, and what you see is that function is now really, really flexible. If you think about the universal approximation theory, that function is able to really tightly match the training data, but it's at the expense of reducing our test error, increasing our test error. So you see, once you train this thing, the training error gets really, really low, but the test error stays quite high. And so we call this an overfit model. So this is a real challenge, is to try and find the neural network that is just expressive enough to fit your data. Yeah.
Case where we have 3 layers with 32 hidden units.
Yeah.
If we would stop the training step after, let's say, 1,000 steps,
yeah,
would we achieve the same as the zero?
Exactly, yeah. And this is actually a technique called early stopping in deep learning, and it's done very often in practice. I have a slide coming up on that. So yeah, good observation. Okay, so let's try and understand these like sources. What we have is an error source here. The final trained network in that overfit case is not actually approximating the function that we want to approximate. So what's that error coming from? Okay, so that error is actually coming from the fact that we're using a finite amount of training data. So when we're training the network, we're only using kind of endpoints here. And we actually call this loss function the empirical loss function. Because it's just a summation over n points here. But the thing that we actually really want to minimize is the difference between the neural network and the true function across all points in space. If we do that, then the network, if it is expressive enough, is going to generalize to every single new point that we test it on. And our training data and test data is going to be the same. So what we actually want to minimize is this thing called the expected loss. And we write it in a kind of a more probabilistic way. We say our training points, X and Y, are just drawn from some joint probability distribution. So these are like, this is, if it's natural data, it's like X is like a set of images, for example, there's a probability distribution over them. And then we want to minimize the expected value of the loss function. So what's that? We basically, for every single value of every possible value of X and Y, we just evaluate what the loss function is with the network at that point. We times it by the probability of those 2 points, that pair of data being true, and then we integrate over the whole thing. So it's just an expected value. But I mean, the tricky thing is we really can't do this in practice. We're training neural networks with like a limited amount of training data in the majority of cases. So this actually, there actually is two sources of error that come about of neural networks. So the first one is approximation error. So we truly want to minimize this expected loss. And we have some true function that has some value of the loss, maybe it's 0, for example. But if we don't choose a neural network that's expressive enough, say just a linear model when we're trying to fit a polynomial, then it's never going to be able to perfectly fit that, even with the expected loss. So there's going to be some approximation error, and this is down to the limited expressivity of the neural network. And then the second source of error is because we're using a limited amount of training data and we're minimizing empirical loss rather than the expected loss. So that's going to be the difference between the neural network, which minimizes that expected loss, which we can never truly get, and the network that minimizes our actual empirical loss function. Okay, so one way to think about this is to think in terms of function space. So what you can imagine is just on like a 2D plane, perhaps, you just imagine that you plot on that plane all the possible functions that are out there that map kind of a vector to another vector. So then you can think, okay, where does my true function? It just places somewhere in this function space, somewhere here. And perhaps that, if we're thinking about fitting polynomials, for example, that function lies on a manifold of function space. It's the manifold of all polynomials, for example. And so I've plotted it as a line here, but I mean, I'm putting this all onto a 2D representation. It could be something else. It could be a plane or whatever. Okay, and then you can think about your neural network as like a space of functions. So the neural network represents a space of functions, and that space is the boundaries of that space is basically all the different variations of the flexible parameters of the network. So if you changed all those flexible parameters, these are all the possible functions that neural network could represent here. Okay, then we can start plotting the different sources of error when we're training our neural network. So the first one I said before, approximation error, is how close can the space of neural network functions, how close is that to the true function? And if this space here doesn't overlap with the true function, then we have an approximation error. So this could be the linear model, for example. And if we go to like a neural network with more layers, then this boundary would expand and hopefully expand into the true function. But then we would only get this if we minimize the expected loss, but we actually minimize the empirical loss. So we also have a problem where we get a neural network which is inside this boundary, but maybe further away from the true function again. Okay. Cool. So then we can plot like our different models in terms of this function space. And so if we think about the underfit model, again, this is the true function here. The underfit model is not very expressive. It's just a set of linear models. So we would think the blue boundary here is very small, and the neural network is just right in the middle of it somewhere, and it's very far away from the true function. So the ideal model, we would choose a model that's more flexible, like the space is larger, and but not too large that the neural network, which minimizes the empirical loss, can't stray away too far from the true function. And then in the overfit case, we're choosing a very expressive model that could represent very many different functions, and the neural network that minimizes it is far away from the true function again. Okay, so another way you can look at this is through using statistics and like probability theory in a bit more precise way. And so what we can do is think about this expected loss again. So remember, the expected loss is the thing that we really want to minimize. The difference between the network function and the true function summed across all possible inputs and outputs. But what we could do is we could say, okay, what's the expected loss, but also averaged over all the possible training data sets that we could give to the neural network. So obviously we have one expected loss if we just train one neural network with one data set, but then we can average that over, we can randomly change the data set with new inputs and outputs, and then get a new expected loss and then average over those. And what is that quantity? And so if you just assume that your loss function maybe is just a simple least squared errors for now. So what we're saying here is h as a function of xd here is just my trained neural network with a particular training data set d. So this is just the neural network trained with a data set d, the error of that with its true labels of the training data. And it can be shown, you just use kind of basic properties of expectations of random variables. You can decompose this into three different terms. And we call these terms the bias of the expected loss, the variance, and the irreducible noise. Okay, so let's think about what those three terms mean. So this is this thing on the left is, what is the expected loss between the neural network and the true data points that we have. So the first one is the bias, and so h bar as a function of x here is the average model. So it's the trained neural network as for a given data set averaged over all possible data sets. So you can just think of this as like training your neural network many times with many different data sets and like averaging the results. And so the bias is saying the error depends on how close that average model is to your true function, or your true function averaged over like your noisy observations. So this is basically the mean of y. If you think about those noisy observations, this is like the polynomial function. So this is kind of saying how far am I away, my best guess at what the neural network is away from the true function. Then the next term is the variance, and it says, okay, given a specific model that's trained on specific data set, how far is that on average away from my average function that the neural network averaged over many data sets represents? So this is the variance. This term is basically saying, if I change my data set, how sensitive is the prediction going to be of the network? How much does it change from its like average prediction? And the final thing is this irreducible noise that we can't beat, and this is because we have inherent noise in the data. So if we fit a function that was a polynomial to a noisy data points, we're still going to have a residual error, which is going to be the standard deviation of those points. Okay, so what you can do is you can try and think of your models like decomposed in terms of their bias and their variance. So if you think about this is like your function space again, and in the middle is the true function that we really want to represent. So a function that has low bias, it means that the average model trained over many data sets is going to very closely match the true function that we're trying to estimate. And low variance means that if we train many, so each blue point here is a model trained with a different training data set. Each blue point here is clustered very closely around the mean of that distribution. So it's not very sensitive to changes in different training data sets. But then we can also have models that have high bias. So that means their average model is maybe not close to the true data set, but low variance and all the different variations. And what you typically find is this sort of relationship between the bias and the variance. It's typically there's a trade-off. And it says that as your bias gets lower and lower, so as your average model kind of better and better gets closer to your true function, the variance, the sensitivity to the training data just increases rapidly. And so and the total error is the sum of these two error sources. And so there's some optimum point as a function of the model complexity where the bias is not is low and the variance is also low. Okay, so how does this relate to those like 3 examples that I showed before? Okay, so this model here, like the set of lines basically has a high bias. Like the average, if you train this line on many different data sets, it's still going to be a line and it's never going to approximate your polynomial. So it has high bias, but it has low variance. Like imagine if I trained on the orange points versus the blue points, I would probably still get a line that's very similar. So that model is not very sensitive to its training data. And if you think about the overfit model, it has low bias. In the, if you imagine training on the orange points and then the blue points and averaging the result, you would get a polynomial that's very close to the true function. But it has high variance. Like this is overfitting to the training data. If I trained on the test data, it would be a very different function. So in a very kind of hand-wavy way, a lot of machine learning practitioners like to think of this, well, the bias is in terms of your training set error, and then your variance is the difference between your test error and your training error. And so what you're really looking for is a low bias and a low variance model. And that would mean where your training test and your test error are very similar, and hopefully both low as well. And for this model, I can never get my training error and my test error to be perfectly 0, like 10 to the minus infinity, because I have some inherent noise on my training points. There's always going to be this irreducible noise that I can't beat, and so that's that final term in the decomposition. Okay, so we have these 2 sources of error. We have approximation error, the flexibility of the network, and the estimation error, so the effect of the training data. So how do we improve it? And that's the next question, really. And basically, what we spend a lot of our time doing when we're actually training neural networks is trying to reduce both our test error and our training error. So if we have high bias, or equivalently, if we have underfitting, the obvious thing to do is to increase the complexity of your model, like expand it in function space so that you try and expand into the true function that you're trying to model. Another way you can do it is instead of expanding the function space, you can just shift the function space, and that would just equate to changing the model architecture, perhaps, instead of maybe increasing the number of parameters or the expressivity of it. Okay, and then if you have high variance, or if you're overfitting, one very easy way to do it is just to increase the amount of training data. And that kind of makes sense. Like the more data that you have, the harder it is to overfit to that data. The final way that you can reduce overfitting is to regularize the neural network. And so that's what I'm going to explain in the next part. Okay, so we have this idea of the function space again. And so I'm going to explain regularization techniques, which is a way to reduce overfitting. So the problem here is that the network represents many functions, and the one that minimizes the empirical loss is like far away from the true model, and it just really fits the training data instead of getting a true function. So one way that we can improve this situation on the right is to, instead of just having any sort of function within this boundary that the neural network can model, we actually try and like put some preference on the specific model that it should try and look for. So instead of changing like the boundaries of the function space, which is like increasing the number of parameters of the network, for example, or changing the architecture, we can instead have that's like a hard constraint. We can have a soft constraint, and we can say, okay, we actually want to prefer like certain regions of this function space. We have like basically a prior understanding of what the function should represent, and we want to prefer models that sit in this area. And hopefully, we would choose this. We would prefer models that are close to the true model. So we have to have some understanding of what the true model is to be able to do this. Okay, so regularization. This is a really important concept to try and understand. It's to restrict the space of possible functions a neural network can learn, or another way of saying it is to prefer certain regions of the function space, or another way of saying it still is, in terms of probability, is to have a prior on the parameters of the network. So have like a preference on what they should be, and therefore the functions that it represents. Okay, so how do we actually do this in practice? There are many different regularization strategies of neural networks and function fitting in general. The top two ways are just the hard ways that I said before. So basically changing your model complexity or the architecture of the network that will shift the boundaries of the neural network here. But the soft ways to regularize, to prefer certain functions given this boundary, there are many different ways. So one is to increase the training data, and as I said before, that makes sure that your empirical loss is as close as possible to the expected loss that we actually want to minimize. And in doing so, that will shift the neural network that minimizes the empirical loss closer to your true function. There are other ways, though, that if we don't have enough training data, we can do. And so I'm going to talk about these 4 different strategies here. So weight regularization, additional loss terms, dropout, and early stopping, which is what you mentioned earlier. Okay, so how do we prefer like functions that fit the true function over other functions that the network could learn? So one idea is to do this thing called weight regularization. And so this is kind of like the idea that the true function that we should learn should be as simple as possible. That's kind of our preference or our prior. So for example, with the polynomial, that is quite a simple function compared to like a really complex function that fits all the training data. Okay, so how do we prefer simple functions? Well, one way to do that is to take out weights, make the neural network less expressive. And so this is what weight regularization tries to do. It tries to prune unnecessary connections in your network. And the way that it does it is to add an extra term to your loss function. And it says, I'm going to penalize not only the difference between the network's output and the training data, but also the values of the weights themselves. So these are the 3 parameters of the network. So you can see here that if all the weight values are high, so every single weight value is like a large number, this loss is going to be very large. But if some of the weights are 0 or close to 0, then the loss is going to be minimized better. And so what happens when you take a weight to 0? You're basically pruning that connection of the neural network. You're getting rid of it, and it makes effectively, if you do that a lot, it reduces the expressivity of the neural network and makes it fit a simpler function to your data. So in terms of like traditional function fitting, this is actually a very well-studied technique, and it's known also as ridge regression if you've done kind of other function fitting methods. And also you don't have to choose an L² loss here. You can also use L1, L0, and it affects kind of the way the weights are pruned as well. So the whole point here is adding an extra term in our loss function that prefers certain models over others based on the values of theta. Okay, so there is a probabilistic perspective that you can take to kind of derive this loss function as well, which is interesting to do. And I actually talked you through this when we were talking about the probabilistic interpretation of supervised learning in last lecture. And so if you remember, when you're thinking about supervised learning in a probabilistic way, we actually want to fit, we actually want to model the probability of y given x given and theta instead of just a function. And what we did before is we said, okay, the probability is just a normal distribution, and the neural network represents learns the mean of that distribution. And then we said, okay, we're going to choose the model, the values of theta that maximize the probability of our training data, given that value of theta. And we showed we just times these normal distributions together if they're identically in distributed points. Okay, so that's good, but it doesn't take into account any like prior understanding of what we think theta is. And so what we can do instead is we say, okay, I think theta, it's just these values of theta should be, the probability of them occurring should be determined by a normal distribution. So if we just take the weights of the network, they should be distributed according to normal distributions. And again, let's just assume for simplicity, they're like identically distributed, and they're normal distributions. And so we can just, the probability of all the weights together is just the multiplication of all the individual probabilities of the weights. And then instead of maximizing the probability of the data given the weights or the values of theta, what we really want to do is get this in terms of probabilistic modeling. We want the posterior of the weights. So we want the probability of the weights given the data, which is kind of the flip the other way around. And this is just given by Bayes' rule, which is the probability of the data given theta. So this is our data likelihood times by our prior divided by, we call this the evidence term, the probability of our training data. And so instead of using maximum likelihood estimation, so maximizing this guy, we're going to use a technique in statistics called maximum a posterior estimation or map estimation to estimate theta instead. So maximizing the probability of theta given d. So if you do this, it's just this product times by this product. We just maximize that. See that the probability of d doesn't depend on theta here, so we can just ignore this term. And if we compose these together, if we take the logarithm of these two things, then we end up with a loss function, which is again the mean squared error plus just the L2 norm on our weights. So it's just a really nice way of like looking at weight regularization in a probabilistic sense. Okay, so we can like abstract out a little bit and say, okay, that was one way of regularizing the network, like with the weights. But we could just choose this to be any function we want. So we can, that prefers certain values of theta over others. And it could also be a function of the training data too. And so we can just think of this as an additional term in the loss function that tries to prefer certain models based on some prior understanding. And so again, there are many different regularizing terms in the loss function that you can use. And it depends very much on your learning problem. So I've got a couple of examples here. Like one is this called so for example, if you're learning to generate images and you want the image to look realistic, but the output of the network is not producing realistic images, you can have an additional term that says I want the generated image to minimize the structural similarity index measure. And so this is a fairly complex function as like a combination of the means and standard deviations inside the image. But at a high level, it gives you like a number which represents like the perceptual quality of an image. And this is very often used as a metric to test image generation networks as well. Another loss function you could do is say, okay, I just want my output functions to be smooth. So what I could do is I say, okay, this is the output of the network y hat here. I'm just going to do a Fourier transform, and I'm going to times it by like a low pass filter. So I'm just going to accept just the low frequencies of that function. And I could add that as a loss term. And then when I'm training the network, I can just differentiate through the Fourier transform to update the weights of the network when we're training the network. And then the final or another idea for a loss function is like a feature space loss. So this is really popular actually, and so this is the idea that if we're training like an image generation, for example, again, and we have a true image and an output image, maybe the difference between the pixels is not the best type of loss function to choose. We're taking a norm in the space of pixels. It might actually be better to take a norm in a different space, which maybe that space is like the space of salient features in that image. So for example, if you took that image and transformed and turned it into like a set of salient features, like using unsupervised learning, for example. And so, for example, that one feature might be how much like a cat it is and how much like a dog it is, or like the textures in the image. If you took a norm in that space as a loss function, you may get images that are like better, and you might be able to train the network better. So one way to do that is to take like a pre-trained CNN, for example, and take a loss function, which is you pass the network through the CNN and take some hidden layer of the CNN. You take a norm on that layer instead, and you would maybe that minimizes these salient features of the image better. Yeah.
What does the D mean in the R mean?
Here, so D is our training data set. Yeah, so in general, we can feed not just the values of theta, but we can put in training data as well.
Lambda in the weight regularization is to say how strong we want to regularize.
Exactly. Yeah, exactly. So this is definitely a challenge of doing regularization. You have to choose like how much regularization you want. And if you over regularize, like if you're doing weight decay, then the network's just going to be zero everywhere. It's just going to have no connections. But if you under regularize, it will probably overfit. And so these hyperparameters, we call them when training deep neural networks. And this is the job of a practitioner, is to choose the hyperparameters that fit the data the best. Yeah, and it's not always obvious how to choose them. I mean, with the weight regularization, it's kind of nice. Lambda here has like an interpretation, which is, it actually falls out to be the standard deviation of your prior of your weights. But we don't always have like a nice kind of explanation of that. Okay, so another technique that is often used is a technique called dropout. This is kind of similar to weight regularization in that it changes the weights of the network in some way. And so the idea is basically when we're training, what we're gonna do is we're gonna randomly set some of the activations to 0. So we're gonna drop, that effectively means we're gonna drop some of the neurons in the network every time we run a training step. So for example, think of one training step. We're going to pass like a training input here, and we're going to get a training output. But we're only going to use the models that are highlighted here. We're not going to use any activations from these 3 neurons. So we're going to, and we're going to, as we go through training, we're going to randomly drop different neurons for each training step that we do. And typically when you're using dropout, you do quite a high level. So you say you'll drop out like 50% of the neurons. And so what does that do at the end of the day when you've trained the full neural network? And what it does is it means that each neuron can't rely on like a single neuron before it, because that could have been dropped out randomly in some training steps. And it also means, conversely, that the neural network can't rely on a single neuron. And so it's hard to kind of understand intuitively how this helps, but maybe it helps like build in some redundancy, like it doesn't overfit to a specific neuron in the neural network. And we typically find this really helps to regularize neural networks and to reduce overfitting. You can actually think of this probabilistically as well, and the neural, when you're training with dropout, it's effectively training an ensemble of models, like an infinite amount of combinations of neurons. And one thing that you can also do, which is often used, is you can actually sample from this ensemble. So you can sample, after you train the network, you can randomly do dropout again and get multiple different outputs of the network. And those different outputs can actually be used for uncertainty estimation. And then the network can kind of say how uncertain it is, given the inputs, what its outputs are. And so this is a really easy way of doing uncertainty estimation in neural networks. Cool. And then events, early stopping was exactly what you realized before. And so this is just the observation that, okay, when we overfit our models, we get a big train and test error at the end of training. But actually in the middle, or when we start off, they're actually very similar. And at some point, they start diverging. And so I'm plotting this trained neural network as a function of training step. And you can see, like, early on, it does actually get a really nice generalizable function that looks like the polynomial. And then it's only in the later steps that the network starts overfitting to that training data. This is actually related to a property which we're going to go into more detail in future lectures of neural networks, which is called the spectral bias of neural networks. And this is the property that they tend to fit the low frequencies in your data much faster than the higher frequencies. And so this is why early stopping works. It fits the low frequencies, which in this case, we wanted a nice low frequency model or a simple model. And so we just stop at the appropriate point, and you can just choose that point just by looking at your training and your test error of your network. Cool. And then the final regularization technique is just to increase your training data. That is always the best, well, not the best, but it's a surefire way of improving the accuracy of your network, is to add more training data. So what about the case when we don't have more training data? And this is very true of many different applications. Well, there are some kind of tricks that you can use to add effectively more data. So for example, imagine we're just trying to do a very simple kind of digit classification of this image, probability of the number, given the image. But imagine with this case where we're only given 9 images, so basically like an example of every class. So how are we going to, we're at a very big risk here of overfitting to those images and not performing well on other new input images. So what can we do to try and improve or add more training data? So one very simple technique, and it can be very effective, is just to augment your training data. And so this just means doing random transformations of your data to generate new inputs. And so these can be things like rotations, crops, adding random noise. This can all help reduce your overfitting of the network. A slightly more advanced technique, and has become very popular in computer vision in recent years, is this idea of self-supervised learning. And so what this is we say, okay, we don't have very many labeled examples. So what we're going to do instead is we're going to do some pre-training task, which is unsupervised. So it doesn't need any labels. And then we're going to take that pre-trained network, and then we're just going to fine tune it on just a few labels that we have. And typically that really improves the performance in like a low data setting. So what is that unsupervised task that we can pre-train the network on? So there are many different tasks you can do depending on your data. But one pre-trained task might be to like take your input image and just crop out a random section of it and get a neural network to predict, to infill that image and predict the output. And so we can just use like one of these types of network, like an encoder decoder structure, for example, and train this using a unsupervised loss. And then we can just, once we've pre-trained this thing, we can just throw away the decoder section of this network and just use this encoder network as our network that we then train using a cross-entropy loss to our classification on our few labels. And so this is a really popular technique, and it's very flexible. Okay, cool. So we'll take a 5-minute break, and then we're going to talk about more error in neural networks.
Yeah, in theoretical direction, we've already seen the connection between overfitting between the number of training steps and number of parameters.
Yes.
And when you're going into a research direction, you can try to quantify quantization and how much the overfitting is. And those eventually become the same.
Yeah. So there's a whole field in statistics, which is like studying generalization of like function fitting, the effect of the training data. And so it's if you're interested, I think a really good book is, we link it on the Moodle pages. It's like the introduction to deep learning. It's like I've got kind of they have some really good like theory in that book. It's a whole area of like provably approximately correct like functions. Yeah, it's definitely worth checking. Yeah, it's not right now. Yeah, it's on. If you look on the course outbound on Moodle or wherever, there's like 2 or 3 books. Yeah.
As a like debate as the low pass filters, will they make more sense with like a high pass filter? You want to have high voltage, high speeds.
Yeah. So
you want to kind of like
yeah. So you could do that. It depends what it depends what you want. It depends what output the network. So if you have this like prior, which is simple low frequency models, then you do a low frequency.
And if you expect that like our problem is high frequency,
yes,
and it can also like a band pass filter or like the expected, yes.
Yeah, exactly. Exactly. You got it. Yeah, go on.
I have one question that is, here you say during training randomly set some activation to 0.
Yeah.
You mean during a specific data set training or in between?
So every training step randomly drops some of the nodes. Okay. So they change every time it's the training step.
And then the second question is kind of intuition, just to say it.
Yeah.
Here, when we do the regularization, yeah, here it comes nice to have our scientific knowledge and our physical knowledge. So we can regularize with our scientific knowledge.
Exactly.
And come to the function.
Exactly. Yeah. So we'll talk about physics informed neural networks next week, and that's exactly what they add an extra term in the last one, which is constraint on our physics.
Okay, I have a question. So this is very
Yep.
It's more about implementation. I mean, as soon as the train of the testers start diverging, probably, I guess, that's what I just
That's exactly that.
Okay, so could we just say as soon as the divergence rate meets some stopping criteria, we stop and maybe go back, I don't know, 10 training observations in order to get rid of all the overfitting we have.
That's exactly what we do.
That's done.
You can choose whatever kind of criteria you want. You can train it up to a set point and then just take a model. Because you could just save the models every time you do every training step, for example.
Yeah.
Or you can do a better criteria that you're talking about.
Wouldn't that use like a lot of data? You can save training.
So you only have to you only have to save the weights of the network. Yeah, the training steps, because that's the model. So it depends on how big the model is. But I mean, it's a good idea, but if you want a model that's like faster than yes, that's right that you're talking about. You're gonna have a large model to make sure that it fits any function possible. It might not be great if it might be a huge neural network. You could actually get away with a much simpler network if you trained it better.
Okay, so I guess if you like to run this neural network, put it in or so.
Exactly.
And then another question is more based on intuition.
Also, sorry, the other thing is this doesn't account for the bias of the network. So the network doesn't like fit the data well, or it doesn't fit the true function, or doesn't have the capacity. It's still going to be great.
What do you mean by that? I don't quite
So remember, a high bias model is one that could never ever represent the true model.
Yes, that's like you just have a linear switch.
Yeah. So there are a few cases where you can get like a high bias, high variance model. So like a model that can never truly fit the function, but also have a high variance. Like the difference between the testing and things. You can like come up with kind of weird examples and like fitting like straight lines, like weird data sets. Okay. So you also have to be careful with that.
So I guess there's no golden bullets.
No, and this is why deep learning is a little like that.
Okay, then the other question I had is if you have like the neural network, then what do you rather change? Do you keep adding neurons in one layer, or do you keep adding layers? Like, if you have a neural network in one layer, and you add the next layer only one neuron, what are the effects of adding one neuron, or just
Good question. So that, again, the challenge with deep learning and neural networks is we really don't have good enough. Basically, every advance is starting to territory results, which is not great. That's not true in I'm very speaking for them. There's a lot of people as well.
Yeah,
but in general, so we generally find that depth is better than width. Oh yeah. So remember that slide I showed in the last week's lecture? I showed deep CNNs versus shallow CNNs. I'll have a look at it. Yes. This is a deep neural network. This is the test error. This is deep neural network. This is a shallow one, and they both have the same number of parameters.
Okay.
So now this is based on image classifications. Yeah. And the way to think of it is like there's like a general belief that the true function is composed of these simpler functions, and that's the prior that we're like using. So that's how that works better. That's the inductive bias.
Okay. So it's also based on.
But it depends on the problem again. So it's very hard to choose.
Yeah. Thank you very much.
Okay. Okay, great. Let's get back to it. Okay,
So I just talked about two sources of error: the approximation error, which is whether the neural network can ever truly approximate the true function. And then the estimation error, which is introduced by the finiteness of our training data. Okay, so there's like an elephant in the room here that I haven't talked about for the whole of the first lecture and this lecture. And this is another big source of error in training neural networks. And this is optimization error. So up to now, we've been assuming that we have this empirical loss. And we're assuming that our neural network minimizes that empirical loss function. So, the mean squared error over our training data. But in practice, this is actually an extremely hard task in its own right. And we don't really ever get to that loss function unless that loss function is very special, say it's convex or something. But in the vast majority of deep neural networks, it's not. So we have to really consider another effect, which is the optimization error on the performance of our neural networks. And so there's kind of like this no free lunch, basically, which is like neural networks can, in theory, approximate any arbitrary function. But there's no guarantee that actually finding that network is a tractable problem. And that's a really important thing to understand. Okay, so then we have to think about another error source. And again, we can look at this in function space. And so remember before we had our true function up here. We had this approximation error, how well a neural network could ever approximate it. Then we have this estimation error. This is from our training data. And then we have one final error source, which is the optimization error. And it means that the final trained network, which is over here, might not ever be close to our true function that we're trying to model. And so we can add these error sources together. We just say the total error is the approximation error, estimation error, and optimization error. Okay, so and as I've tried to show you in so far in the lecture, how do we minimize each of these three different sources? We minimize them using different strategies. So the first one, we choose a larger hypothesis space, so like a neural network with more free parameters, for example. Second one, we add training data or use one of these regularization methods. And then the final one, which I'm going to talk about for the rest of the lecture, is trying to improve the optimizer so that it can optimize the neural network weights to get as close as possible to this empirical, the neural network, which minimizes globally the empirical loss. Okay, so you can actually have a look at these like loss functions of neural networks, and they're really fascinating to, I mean, there are websites out there where you can actually explore these loss functions. So how do you even visualize a loss function? Remember, the loss function is a function of the neural network's parameters. And I said before, like neural networks have millions, even billions of parameters. So that loss function is in an extremely high dimensional space. So it's actually even a challenge just to look at what the loss function looks like. And so one way you can do it is you can create like a 2D visualization. And what you do is you can just think of a point in that parameter space. That's basically just a single neural network function. And you can take two random directions in that parameter space. You just randomly sample, say, and then you measure the loss function as a function of those two directions, and that gives you like a 2D visualization of the loss function varying across those two parameter combinations. So this is what it would be mathematically. The loss function is a function of alpha and beta here, which is just where u and v here are two randomly sampled directional vectors in your parameter space. And so, yeah, people have done this. So this, for example, is a 2D visualization of the loss function of a ResNet. So this, we're going to explain what our residual network is later. But this is a model that's trained on Sci-Fi 10. So this is image classification of natural images. And they took this expansion of the loss function around the optimal solution from the optimizer. So this is the minima that the optimizer found. And obviously you can see it's incredibly complex. It has lots of local minima, saddle points, lots of interesting things going on. So there are two big problems when you look at these loss functions that kind of occur, particularly when you're training neural networks. And so the first kind of problem when you're using an optimizer, and it's actually kind of counterintuitive, is in many areas, your loss function can be completely flat. So instead of looking like this, where you have a global minima, it's just flat everywhere. And if you think about how gradient descent is going to work on that, it's never going to even move anywhere. Your network's going to be stuck on one particular sort of kind of model. So why can this ever be possible? Or one of the biggest reasons is the choice of the activation function that you use. So, for example, this is the tanh activation function, which I showed last lecture. And remember, I was saying activation functions are really important because they introduce nonlinearities into the network. This is what allows them to model like arbitrarily complex functions. So we have to have these kind of nonlinearities to model these. But so imagine if you fed in an input that's actually like very negative or very positive. So x is -5 or +5. Then tanh x here is going to become saturated. Basically, the output is always going to be 1, whatever the value of the input is. So then if you start thinking, okay, the chain rule, when we're training neural networks, we need gradients to the network. And so at some point, we're going to evaluate the derivative of the activation with respect to its input. And what you can see out here is the derivative is just 1. Oh, sorry, the derivative is 0 for every value of x. So that means that our derivative is doesn't depend on the value of x anymore. It's just 0 everywhere. And in turn, that just means that loss function is also 0 everywhere. And you can just think of that as the network just getting fully saturated. So this is a really important point, and a lot of people forget this when they're training neural networks, and definitely remember this when you're doing it yourself. You have to make sure that your inputs are normalized properly between -1 and 1 if you're using these types of activation functions, so that the inputs always, so that you don't just get 0 gradients everywhere. And this can have a really big effect. If you don't do this, this has a really big effect on the performance of your network. Okay, so the next interesting thing is, okay, say that we've normalized our data properly, so that you know, we're falling within this this part of the tanh function. The loss function can still be flat even if you do that, and this is another problem of neural networks, which is called vanishing gradients. So how does this work? How is this possible? So what we need to think about is these deep neural networks, and we're taking it when we run a deep neural network forward, we're taking an input x, and then we're just we're transforming it into a hidden vector, and then we're transforming that hidden vector again and again and again and again. And what we should think about is, how do the output values of those hidden states vary? Well, actually, what's more interesting is, how does the variance of those values change? So do the values, like, generally the variance of them stay the same? So they just, you know, the inputs are between -1 and 1. Do the hidden values stay -1 to 1? Or do they increase generally, or do they decrease? So we can actually just figure this out with a couple of assumptions. So just think about a single neuron in a MLP. And so without any activation function. So we're just going to simplify the problem for now. And so then the output of the neuron, so the hidden value, is just the summation of the weights times by over the inputs of the neuron. Okay, so then let's imagine that x is just like a random variable. So and we're going to say it's like distributed between -1 and 1. So its values just vary between -1 and 1. Okay, and let's also say that the weights, we're gonna when we initialize the network, the weights are just going to also be randomly sampled between -1 and 1, say. So then we just have an output here, which is just a function of these random variables, and it's just timesing and summing them together. And so what we want to understand is, what is the variance of y if it's a random variable based on the variance of these things. And so we can just use well, we need to make a couple of assumptions. The first is that the mean of the weights is 0 and the mean of x is 0. That's generally true if we sample w from a normal distribution and x from we normalize it between -1 and 1, and we assume all the inputs and weights are independent, etc. If you just use like basic properties of the variance of random variables and combinations of those variables, you can very easily show that the variance of y is this expression here. So it's the multiplication of the variance of w and x but also, and importantly, times by the number of inputs to that neuron. So remember, the neuron has like one output and it has multiple inputs in a fully connected network. So what you're seeing is, the variance of y is not necessarily equal to the variance of x. It actually depends on the variance of w and the number of inputs. Okay, so we can actually explore this like empirically a little bit. And so what we can do is just imagine setting up like a fully connected network with like 5 hidden layers, and each hidden layer has the same number of hidden units. So the width, it just stays the same through the network, and just no activation function for now. And then, as I said before, we're going to make sure the inputs x are just normalized between -1 and 1. We initialize the weights from a normal distribution, so mostly between -1 and 1. And then we plot a histogram of the output values of each layer. So we just histogram all those values of those 100 values of each layer. And so then we show the histograms for different weights that are drawn from different normal distributions. And so this is weights drawn from like a very tight distribution with a small standard deviation, and these are ones from a much larger standard deviation. And you can see with the small values of the weights, the outputs of the network just decrease to 0 very quickly. And if the weights are too large, then they grow very quickly. And then there's some sweet spot in the middle where if you choose the weights, initialize the weights in a nice way, then the outputs follow the same, have the same variance as the inputs. Okay, and we know actually what how this should look based on that expression that we derived earlier. So what we want is for the variance of y to equal the variance of x. And for that to be true, we need this thing to be 1. And so that says variance of w just needs to be 1 over the number of inputs to the neuron. And if it's less than that, then you can see that y just decreases exponentially with the depth. So we're just multiplying this by to the power of d. And if it's less, then it grows exponentially. Okay, so how does that affect the loss function? I said before, this effect makes the loss function like flat or 0, and it makes it really hard to train. Well, I mean, the reason is if all of our outputs of our neural network become 0, then our gradient of our loss function also just tends to 0 because the network's basically 0 everywhere. But conversely, if the outputs all just go to infinity, then if we're using a tan H activation function, you can imagine like on this layer, the tan H function just gets saturated because its inputs are very large. And so then you have that saturation issue in the gradient, and then you also get a flat loss function. So we really want to make sure that we initialize our networks properly using weights in the middle here. So what we really need to make sure is we choose the weights with the variance that is 1 over the number of inputs of the neuron. So for example, for this network, each neuron has 100 inputs in the hidden layers. So we want to have the variance to be 1 over 100, or the standard deviation to be the square root of that, which is 0.1. So this turns into an initialization strategy called Lacan initialization. And this realization really improved the depth of the neural networks that we could actually train. Okay. So we were thinking then just about the forward pass and how the values in the neural network change as we go from layer to layer. And we want to make sure those values approximately have the same variance. But we should also think about the gradient itself. Like when we're evaluating the loss function, we're using the chain rule, right? And so we're doing a back propagation. We're going backwards through the network and multiplying our gradients together to get a final gradient of the weights at the output. And you could think of that as an operation where at each multiplication in the chain rule, at each step in the back propagation, we want to make sure our gradients are like distributed nicely and stay, and their variance of those gradients also stays approximately constant. So you can actually do the same analysis, but based on the back propagation algorithm rather than the forward pass of the network. And it's actually fairly simple to do. Again, if you think about this is one single neuron. This is the output of the neuron, the input. And then remember our back propagation algorithm is trying to figure out the gradient of the loss function with respect to x at that point in the network anyway. That's what the chain rule is evaluating. And we just decompose this into the derivative of this with respect to y, and then derivative of y with respect to x. So this is just the chain rule. Yeah, for this particular output, this is what it looks like. And so what we want is this derivative with respect to x here, the variance of this guy, to be similar to the variance of this guy, which is the gradient before that layer. And so again, if you assume that the variance of these are like random variables, etc. again, then you have a very similar relationship, but based on the gradients rather than the inputs and the outputs of the network. And so the only difference here is because we're backpropagating, we're going backwards. These variances depend on the number of outputs of the neuron rather than the number of inputs. And so then we end up with this expression that we want the variance of the weights. If we want this variance here of the gradient of the input to be the variance of the output, we want the variance of the weights to be 1 over the number of outputs of the neuron. Okay, so there's this like kind of imbalance between balancing the variance of the forward pass and the variance of the outward pass. And so one good compromise is to choose like the harmonic mean of these two conditions. So this kind of the average or the inverse average. And this lands us on something called Xavier initialization, which is like, I think, the default initialization in TensorFlow for a fully connected network. Okay, cool. So what we're realizing is initialization of your weights of the network, even before you trained it, is a really important thing. And you really have to think about it, and it affects the performance of your network. Okay, so then another kind of trick that we can do is, the whole point of this was to make sure that the variance of each output of each hidden layer stays approximately similar. Or instead of asserting that when we initialize the weights, we can just assert that when we're training the network. And so what we can do is use this thing called batch normalization. And so remember, when we train neural networks, we're not just feeding in a single input example, we're actually feeding in a whole batch of training examples. Ideally, we would input all of our training examples, and we sum the loss function over all those examples. And so what we can do is we can say at some hidden layer, we can just take the hidden values for each training example, and we can just compute the mean and the standard deviation across the batch of examples of those values. And what we were really hoping is that that mean and standard deviation is going to be a mean of 0 and a standard deviation of 1. And if it's not, well, we can just take the output of the hidden layer, which is y here, is x here, and we'll just subtract it from those batch statistics, and we'll normalize it just to be between -1 and 1. Just by using this normalization of our batch statistics. So these values are computed on the fly as you're training the network based on the training examples. And so then you can see that the output of the hidden layer is normalized nicely and exactly normalized as you would expect. So this is called batch normalization. There's a couple of other things. We also add a couple of free parameter here called gamma and beta. So these are extra trainable weights that we add, and this just allows the network, if it thinks it's important to actually change the variance of your inputs and outputs of the hidden layer, then it just allows the network to reverse the normalization if it wants to. But typically we'll just initialize this to 1 and this to 0, and it just adds a bit more flexibility. And yeah, in general, this is a very commonly used technique, and it does allow you to use neural networks which are kind of initialized using many different strategies, and they can still perform very well. There is actually also another body of research which actually just considers this a regularization strategy. The difference here between just initializing your weights is that when you're using batch normalization, you're actually changing the architecture or the forward function that you're running the network through. And so that is actually regularizing the network in some way. So it's kind of interesting to think about it more deeply as well. And then one other subtlety that you have to be careful of is, okay, if you're averaging over that current training batch to compute these statistics, what do you do when you want to have a single test image once you've trained the network? And so once you've trained it, what you typically do is you compute like running estimates of these values, like means and averages, and then we just fix them to be those estimates when we come to test the network in a test step. Okay, and then there are many different ways so all of these different ways I'm talking about is to try and manage the gradient to get like sensible gradients when we're training our neural network. So one way is to initialize the weights, another way is to use batch norm. This is another way to make sure that our gradients are nicely flowing through the network. And this is called residual networks or ResNets. And so the idea here is, this is a really important concept when you're designing neural network architectures, and it's this idea of residual layers or skip connections. And so what we had before is typically we would just have an input, we would pass it through a function, that would be the output, and that would be the layer function. What we do instead is we say, okay, the output of the whole layer is like our layer function, but then we also add it to X, so the input. Okay, so this X, adding to X here is what we would just describe as like a skip connection here. So you see the output here is depends on just X and also the layer. Okay, and so how do you intuitively think about this thing? Well, in this case, now when you train the network, the layer is actually just learning a residual correction of the input. So this layer function learns to like incrementally improve the value of X. So it could still be 0. For example, maybe it doesn't learn anything and it just learns an identity. So the whole layer learns an identity. And so then the inputs would just equal the outputs. So then when you think about back propagating through this layer, if you just take the chain rule again, so dl by dx, it's just again the chain rule, and if you just use this particular value function of y, function for y, you see that the derivative after the layer is just the derivative of L with respect to y plus df dx. And if f is 0, you still get a nice strong gradient flowing through to the the layer before it. So you don't get any errors with gradients flowing through the network. So people like to think of this as like a highway, like a gradient highway here, and then the layers like learn like a small correction or residual correction to the inputs. So these types of networks, ResNets, are super popular for where your input is like similar to your output. So for example, if you're doing like image segmentation or like super resolution or image denoising, these sorts of tasks. And they really allow you to scale to like really large numbers of layers because the gradient is so stable. And actually, the network itself can actually learn the depth that it needs to learn because at some point it will just learn layers that are just zero everywhere. Like it doesn't need to improve on its result. And so that's a really cool idea as well. So an example of a ResNet. So here's some examples of some ResNet architectures. So this is from, on the left here is the original ResNet paper. And so they compared, so you can see, you can start training networks which have like tens, hundreds of layers. And this is generally the trend is to go to deeper and deeper neural networks. And so you can compare like the test error here on the left here is just a convolutional neural network which doesn't have these skip connections. So this plain network here. And then on the right is the same network just with skip connections added. So a residual neural network. And you can see that the plain neural network here like doesn't, when you go to 34 layers, doesn't perform any better than 18. In fact, it performs slightly worse. But then if you look at the ResNet, because of this learning incrementally, you get a big improvement going from 18 to 34. And so ResNets really push the accuracy of like standard classification tasks in image classification, like in ImageNet, they were really on top of the tables for a while. Another really popular architecture or example of a residual network is this thing called a UNet. And so this again just maps like an image to an image. But usually what the UNet does is it also has these like these convolutional layers which reduce like they have strides that are large, and so they reduce the input image down in size. Typically that down to some latent vector here which doesn't have any image dimensions, and then it expands it back out again with these like transpose convolutions, so the opposite operations. But the important thing is they have these skip connections at each kind of scale of the network. And this type of design just turns out to be really useful and really powerful for doing like image segmentation tasks, or any kind of image to image map where you have some kind of multi-scale features in your image. Okay, so problem 1 was that the loss function was 0 everywhere. Problem 2 is, if you think about that complicated loss function I showed you at the start, is the opposite, is that the function is super complicated if you've normalized and initialized properly. And it usually always pretty much has lots of local minima and really complex landscapes. So I said before, we train neural networks with gradient descent, but standard gradient descent just steps in the gradient direction, and will always converge into a local minima if you're just doing gradient descent. So you see here, if you start here, once you get to a local minima, the gradient's not going to move anywhere. And so you're stuck in your local minima of your loss function. So we need to do better than gradient descent, and there are many other ways, optimization algorithms that improve on this kind of standard method. So one way to improve is to increase your learning rate of the gradient descent, or alternatively, the step size is the same thing. So instead of taking small steps to try and like gradually end up in my minima, we take really large steps to start off with, and we hope that this kind of like bounces around in the loss landscape, so it tries to explore it a little bit before going into like a local minima. And you can see you can start like jumping over saddle points and other parts in the loss function if you step large enough. But the problem with this is once you get to the global minima, you can start bouncing around in it and never get to the minima. And you can even bounce out of it as well if you step too far. Yeah, exactly. So what we typically do is we reduce the learning rate with the step size. So one way to do it is just to exponentially decay it. And so that you can think of that as like initially exploring the loss landscape, and then when we found like a nice minima, we'll just descend nice and slowly into it. You can obviously come up with more sophisticated variants of this idea, and so you can have like adaptive or intelligent learning rates, which like vary your step size based on some measure. So I mean, it could be how large the gradient is, the curvature, the value of the weights. Like there are many other kind of adaptive learning rates you can choose. Okay, but this is the main way that we actually do it, and typically used is to use stochastic gradient descent. So everything I've been saying before, we're assuming that we're minimizing this loss function, which is a mean squared error, and it's summed over all of our training data. So n here is like the total amount of training examples we have. But think about that. If we're going to train on like a massive data set of images, then it's evaluating this loss function is really computationally expensive. Like we have to run a network through like 1,000 images or 1,000,000 images, and then evaluating the gradients is going to be a really complicated or really computationally expensive operation. So the compromise is just to take a small batch of images. We call it a mini batch of images, say 100 images out of our training data. And then we just evaluate the loss function instead on a subset. So just like B training points. And then we compute the gradient with that, and then we use that in gradient descent. And so that's what we call mini batch stochastic gradient descent. Okay, so what does this do? Well, if you think about that, if you're just using a subset of your training points, your estimate of what the gradient of the loss is like a noisy estimate. It's not the true estimate. It's going to have some noise based on the points that you choose. And so what does that do when we're doing gradient descent? We actually start choosing directions which are like slightly noisy and not exactly the gradient direction. Now that sounds like a bad idea, but actually that turns out to be very useful because it allows the network again to jump over these like saddle points and get out of local minima. It's like a noisy exploration. So yeah, this is a really popular way of doing it. It produces noisy estimates, but allows us to escape local minima, and it's way more efficient than doing like full gradient descent. Batch sizes of 100 versus 1,000,000, and yeah, we widely use this in practice. Yeah.
Is it possible that with different datasets you find different minima?
Absolutely. Yeah.
In this situation.
Yeah, so this comes down to the kind of estimation error that I was talking about before. Like one source of error is the training data set that you choose. And so you just have to be very careful. I mean, you can use regularization, for example. You have to be careful with the data that you have. Okay, but actually the one optimizer that I would say is the default for many deep learning practitioners is the Adam optimizer. And so this is gradient descent with a few more tricks up its sleeve. And like I said, we usually use Adam with this mini batch gradient descent. So the gradient directions are noisy. And so Adam is actually, it's just gradient descent. So you're taking your gradients and then you're kind of modifying them a little bit. And I'll explain what these modifications are. And then we take this gradient and then we just step in the gradient direction, again, with a step size, and we update thetas just as we did before. So the interesting thing is, like, how do we update these gradients before we take a step in the gradient direction? And so we have these things called moments, which are, again, they're just computed given the gradient. And we have these parameters, which are just scalar parameters here. So what are they actually doing? So there are kind of two key ideas in Adam. The first is that we should keep some momentum when we're exploring the gradient space. So people think of this as like a ball, like rolling down a hill. When it gets to like a local minimum, it shouldn't stop there. It should like go up a little bit and maybe go manage to get up past the local minimum down into the global minimum. And so how would you do this in gradient descent? So this would just mean that you don't just use your current gradient estimate, but you also keep in mind or remember the gradient before. And you actually, what you do is you compute like a running average of your gradients. And so you have some memory of the previous gradient and you take a step in like an average direction. So this is exactly what this function is doing here. M is just our exponentially, it turns out to be an exponentially weighted moving average of our gradient. And we choose beta is basically a forgetting factor, like how much do we want to remember our previous gradient values. That's the first idea. Then the second idea is we want to choose an adaptive step size. So we want to step not just based on the magnitude of the gradient, but or we're going to adapt the step size based on the magnitude of the gradient. So what we do is we take M here is like our moving average of the gradient, and we divide it by V here, which is the gradient squared. So this is basically just the magnitude of the gradient. So we're saying to take our gradient and divide it by its magnitude. And so you can think of this thing here as basically a normalized kind of vector that we're moving in that doesn't actually depend too much on the steepness of the function. And again, you can also do like a running average of this magnitude instead of the specific magnitude at that point. And so that's how Adam works. It has these two key ideas. And then there's one other thing here, which is a bias correction. And this removes the effects of initializing the gradient and the step size to be 0, which is what you initialize them as. Yeah, so then you can plot how these optimizers actually look. If I'm trying to optimize this very simple loss function here, which has a global minimum and a local minimum and like a little hill in the middle. And you can see like gradient descent is obviously going to stop in the local minimum. But both gradient descent with momentum and then Adam, which is like building on that, they both have some energy to get over that hill. Okay, so that's gradient descent. They're kind of like the main tricks or changes that we make to improve the optimizer. There is another idea that you can use, which is, okay, we're just to search the loss landscape. At the moment, we're just using gradients of the loss function, but there's actually a lot more information of that loss function that we could use to help us choose where to explore in the loss landscape. And so what other information can we use? One is to use the curvature of the loss function instead of just its gradient. So what I mean by curvature, I mean it's higher order derivatives of that function. And so you can start thinking of using more and more derivatives of your function to help you explore the loss function. So one way is to go from a first order method, which is gradient descent. to a second order method, which uses second order derivatives. Okay, so how can this help us? How would we design an algorithm? So a useful way to think about this is to think about the Taylor approximation of your loss function around some point A. So this is just like a generic function. This could just be a generic function. And we know from Taylor approximation that around this point A, so this could be like the current values of our parameters, for example. The function can be decomposed in terms of like a linear function and then a quadratic function here. And the gradient of the linear function is just the gradient of the function, and then you've got the second order gradient here. So if you plot this approximation of your function around a point here, you see the linear approximation, first order approximation is the straight line, and the second order is the quadratic. So how would a second order method work to optimize optimize the loss function? So instead of making a step in the gradient direction here, instead we make a second order approximation to that function at that point in that current parameter point in the loss function, and we step towards the local minima of that second order approximation. So we take a step towards the minima of this quadratic. So this is known as a second order optimization algorithm. And your update rule, so if this is the value of theta, the current value of theta, then we just step towards, and we know analytically what where the minima is of this second order approximation. It's just given by the derivative over the second order derivative. Cool. So I showed that for a 1D function, but when you go to multiple dimensions, remember our loss function is a high dimensional function. We're actually talking about the Hessian of our loss function, and we need to invert the Hessian and then times it by the grad of the loss. Okay, this sounds great, and these algorithms often converge much quicker than gradient descent because they're using more information of our loss function. But there is a big computational cost that comes with them. So in particular, this Hessian matrix here, when you're doing multivariate optimization, this is a P by P matrix, where P is the number of parameters, number of theta values we have here. So if we have a neural network which has 100 billion parameters, then we have 100 billion times 100 billion Hessian matrix, which is absolutely intractable to compute. And so how we actually do this in practice is we have to use some approximation of the Hessian and also its inverse. And there are many approaches out there, and one of the popular ones is called BFGS, or even memory limited BFGS. And so these just fall under a class of what's called quasi-Newton methods. Okay, so we have like 10 minutes left, so I realized that was a lot of information to take in. So I just want to end it by talking about this state-of-the-art algorithm that has taken the world by storm over the last couple of months. And this is ChatGPT. And the point of this is to really show you that everything that we've learned up until this point can help us, it allows us to understand these really complex models. And they're all based on these like principles that I've just been teaching you. Okay, so what is ChatGPT? So it's a model that is a sequence-to-sequence model. So, and it's based on natural language. So you give it an input. Typically, when you're dealing with it, you give it a question or some sort of prompt, and then it gives you an output prompt. And the really amazing thing about ChatGPT is it gives you like really intelligible answers for the most part. Okay, so what is this model? How does it work? How do we train it? That's the question. Okay, so ChatGPT is trained on a massive corpus of tokens, or so we have a training data set here, D, which is just a sequence of what we call tokens, and N here is the number of tokens, and this is extremely large. And so this is just a sequence, and each token could be, for example, like a word or a letter or like a comma or something like that. And so you can imagine like all of Wikipedia is just one big sequence of these tokens. Okay, so then we have a neural network. ChatGPT is just a neural network. And what are the inputs and outputs to that neural network? So the input of the network It's just a subsequence of D. So for example, like a random sentence that's extracted out of Wikipedia. So you can write it as this, like xi to xi minus k to xi minus 1. So this is length k, for example, sequence. So we have to fix this, and this is like a choice of the model design. It's like the length of the input sequence. Okay, and then what do we want the network to output? So the output is just going to predict the probability of the next token given this sequence. So it's just an autoregressive task, predicting the next value based on the input. And I'm just going to say this probability of that next token is just given by the neural network and just the output of that network at that token. So this is just the output of the network here would just be one massive vector, for example, where each element tells you the probability. Each element represents a token, and it tells you the probability that that token is the next in the sequence. So this is basically just standard classification. Like, given an input, what is the probability of the output being of this class, this token? So the network is just trained using a standard cross-entropy loss. And this is exactly the loss function that I derived and showed you in the last lecture last week. Cool. So that's going to give us like a question. It's going to give us like the first letter. So it's going to give us like T or there if the token is the word. So then how does ChatGPT actually generate the entire like output sequence? So all you do is once you've generated this word, the next token of the sequence, you just concatenate that to your input, and then you feed that as the input to the network, and you just recursively get a prediction of the output of your question. They also do a bunch of other additional training steps after they've done this. So this is pretty unsupervised as well. So all you need as a data set as input is Wikipedia or whatever corpus of data that you're training on. And the cool thing is that even though it's trained on like sequences of Wikipedia, like when you ask it a question, it can still, the model is general enough to like actually intelligently answer that question. And that's the really cool thing that kind of emerges from this model. But they have a bunch of other training tasks that they use. Like they can pre-train it on like specific tasks. Like if you give it a bunch of questions and answers, then it can like fine-tune on that data set as well. The latest version of ChatGPT also does a reinforcement learning cycle where it has human feedback inside of it as well. Cool. So that's how it's trained. So what is the model itself? And so ChatGPT uses an architecture called a transformer, and this architecture has been really popular in the last like few years or so. Okay, so that sounds scary, but let's try and make it simple. So again, transformer is just a neural network which is composed of layers. It's the same as we've been talking about before. And so what we have is our input text here, our output classification prediction here. And then in the middle, we have a bunch of layers, and we call these blocks. So this is like 4 layers, and then we just make that into a block, and then we just have lots of these blocks composed together, like times by 12 for the first version of GPT. Okay, so then we need to understand what are each of these layers. So we already know about some of these layers. So the feed-forward layer this is just a feed-forward layer, MLP, as we've been talking about. These little plus symbols are these like residual or skip connections, which I also told you about. And then the layer norm is like a variant of batch normalization. So we already understand the majority of this architecture. The kind of interesting thing is this thing called attention. And this is what makes a transformer, is these things called attention layers. Okay, so let's try and understand what attention is. Okay, so there's this really seminal paper called Attention is All You Need, and claiming that, in fact, attention layers are super useful for like many different tasks. And it has turned out that transformers are very, very popular, and particularly for like natural language tasks. So attention is fundamentally a sequence-to-sequence operation. So remember, like our input here is like a sequence of text. And what the layer is going to do is it's going to produce another output sequence here. So something like akin to another text sequence. Okay, so how does it work? So what you do is, well, first of all, instead of having like actual text, you generate some encoding of that text. So you turn this text into like a vector. And the way that you do that could be like another fully connected layer, or it could be some like clever tokenization of your words, like word to vec, for example, is a way to do it. Okay, and so then from this embedded vector here, this single vector, we're going to produce two more or in fact 3 more vectors, and these are produced by fully connected layers. So this is another vector here, Q, K, and V down here. And so we give these vectors names. We say the first one is a query vector, the second one is a key, and the third one is a value. Okay, so we've done that. We've created these vectors. The next thing we do is we compute a score. And so we basically take the dot product between Q1 here from this input sequence and the dot product from the keys here. But we do this dot product across all the keys of each of these input tokens. So this box here is showing you just what happens to the output of the final sequence here, this first element of the sequence. So what is this score doing? It's basically saying, well, we know the dot product is the similarity between 2 vectors. So it's saying how similar is my query in my first token here to the keys of each of my separate tokens here. And this will give me a score. So then we pass that score through like a softmax layer. So that's just saying normalize the scores so they sum to 1. So then you can think of it as like it's not a probability, but like a similarity measure. And then you just times each of the values of each of these sequences by those scores, and then you sum them together to get the output. Okay, so what is this actually doing? Like intuitively, why is this interesting? Well, it's allowing the output element of the sequence to attend to different parts of the input sequence, and it can attend to them with different weights. So it can say, I care mostly about this sequence and the values of this sequence, rather than the values of this part of the sequence. And that's really useful because it allows the network to like model like really complex relationships between different parts of the sequence. So for example, it is a dog. It's really important to understand when you're like parsing that sentence that it refers to the dog. And so in some way, maybe it would learn like to attend to this part of the sequence closer when it's processing this token of the input. Okay, so you could write that mathematically, and you just say, here's my input. Each of my separate tokens is xi here. My query, my key, and my values are just fully connected versions of those, so like projections of those. And then my final output here is just this big matrix operation, which does these individual scores and softmaxes across all of the different elements. Yeah, and basically with that, now you know exactly what the architecture of GPT is. You know how it's trained, what loss function it is, and the training data. And hopefully you can see that actually this is not a scary thing, and it's actually very simple enough to understand how it works. And so much so, if you're really interested in GPT and training your own, Karpathy did a really good GitHub repository. It's like a minimal version of GPT written in PyTorch, and it's really useful for like educating yourself on how it works. So it's just like a couple of 100 lines of code to reproduce GPT. Okay, so I realized that was a lot for this lecture, and there's a lot to kind of go away and condense into your brains. But at a high level summary, there are 3 important sources of error when we're training neural networks, and we really have to think about them to get the best performance possible. The approximation error, the estimation error, and the optimization error. And we can modify those. There are different strategies depending on which error source is largest. To reduce the approximation error, we should change the architecture and the expressivity of our hypothesis space. To reduce the estimation error, use regularization or improve our training data. And then optimization error, we have to change our optimizer. And like I said, there are many strategies that you can choose for these. So yeah, thank you for listening. See you next week.